Hey guys, welcome to this WACE Academy online lesson on the vector nature of gravity. This will be covering dot point number 6 of the physics syllabus, subunit Gravity and Motion. This lesson will be fairly simple and will begin with the basic theory before moving on to two examples. Now we already know an object within a gravitational field will experience a pulling force towards the center of mass of the object creating the field. Gravitational fields are created by any object with mass, no matter how small, and so at any time, an object will have multiple gravitational forces acting upon it. Okay, but if we have multiple forces, how do we add them all together to find the total force? If they're acting in the same direction, that's great. We simply add them together, such as when the sun and moon are aligned and their gravitational pulls are added to each other. But what if they aren't acting in the same direction? Well, when we talk about the vector nature of gravity, what we're saying is that the individual forces can be broken down into two separate forces acting in perpendicular directions. Let's take a look at an example. Imagine a satellite floating in deep space with two nearby planets, Planet A and Planet B, each providing a force like so acting on the satellite, 600 and 800 newtons respectively. We are then told that there is a 90-degree angle between them. Now, in order to find the overall force acting on the satellite, this is what we must do. Firstly, draw a diagram of the forces we already know and the overall force we want to find. Just by looking at the forces A and B, we can tell that the overall force is going to be somewhere in this direction between the two of them. Next, we're going to rearrange these lines, which represent the forces, to form a right-angled triangle. Begin by choosing and drawing out any of the two forces that we already know, A or B, and then draw the second force. Then add the final hypotenuse to the triangle, which will be the overall force, the one we're trying to find. So the next step is to calculate the angle of the overall force, which we can do using trigonometry. So labeling the triangle and subbing in the values of forces A and B, we're left with tan theta is equal to A over B. Therefore, the final angle is 36.9 degrees. And so this is the angle which we can use to find the length of C. We'll use C and force A, which means we're going to use the sine function, which results in 999.3 newtons. Therefore, the overall force acting on the satellite is 999.3 newtons. There are other scenarios where the same concept applies. Imagine a 2,000 kilogram car rolling down a frictionless incline of 15 degrees, and we are asked to find the magnitude of the force acting on the car in its direction of motion, so down the incline. So gravity is always acting downwards like usual, and the car's motion is down the incline, and friction acts against the direction of motion, but we're told it's zero. And so we're left with a diagram like this. So to begin, let's calculate the forces of gravity on the car using F is equal to ma, or F is equal to mg since gravity is the acceleration. So 2000 times by 9.8 is 19,600 newtons downwards. For the next step, let's draw out a force diagram. That triangle diagram we just did with the satellite. Now in this case, we're told the angle is 15 degrees, and so we're trying to find this force, which we'll label Fm. And so from here, we can see that we need to use the sine function again. Once we've set that up, simply sub in the values, and we'll find Fm is equal to 75,728.58 newtons, which will round to two significant figures. That brings us to the end of the lesson. I hope you enjoyed it, and I'll see you next time.